Hi, my name is Joysan Osteen. I'm Aylha Pferschy, and today we will be titrating 10 milliliters of 0.50 molar HN3, also known as hydrozoic acid, with 15 grams of NaOH dissolved in 1 liter of water. So firstly, we will have to calculate the molarity of our NaOH given our mass. So to do that, we have to do a table conversion, starting with our amount of 15.00 grams NaOH. We have to calculate the number of moles that we have here. So we know that there are 39.998 grams per mole of NaOH. That's 1 mole. So upon this conversion, we find that there are approximately 0.375 moles of NaOH, which is dissolved in 1 liter of water. And so we derive the molarity 0.375 molar. Another thing we have to find is our equivalence point, and we do that by utilizing the equation M1V1 equals M2V2. So in doing this, we have 0.5 molar of our HN3, and we start with 10 milliliters, which I will convert to liters by dividing it by 1,000 milliliters, equals 0.375 molar X. And this X, we are solving for our volume in liters. So once we do this calculation, you will divide this by 0.375. We find that X equals 0.13333 liters, or 13.33 milliliters. This will be our equivalence point.
Okay, so the next step is to find the initial pH, and for that we need to know the Ka and pK values, which we find from the chart given, and the equation to find the pH, we have to start with the concentration of H3O, which equals the square root of the Ka value, which is 1.9 times 10 to the negative fifth, times the molarity, which is 0.50 molar. And with that, we get 0.003082207 for the concentration of H3O. With that, we can find the pH by finding the negative log of that value. And we find that the initial pH of the acidic solution is 2.51. And to confirm that, you have to use the 5% assumption. So to check it, we put the value of the concentration of H3O over the molarity. And then multiply that by 100 to get percentage. And you get 0.62%, which is less than 5%, so the assumption is correct and valid.
So as we found before, our equivalence point occurs at approximately 13.33 milliliters of added NaOH solution. So to calculate our pH before equivalence, we'll be adding 5.00 milliliters of NaOH solution. So we'll be adding 5 milliliters of NaOH solution. So first and foremost, before we do our calculations and we set up our BCA table, we have to calculate the number of moles of HN3 that we have, as well as the number of moles of NaOH that we have. So we know that we have a molarity of 0.50 for acid. We multiply that by 0.01 liters, which is what we started out with, 10 milliliters. And we obtain 0.005 moles. For NaOH, we found that our molarity was 0.375. And we will multiply that by our added amount of solution, which is 0.005 liters. Upon doing this calculation, we find that we have 0.001875 moles of NaOH. And to clarify why this calculation works, it's because molarity equals moles over liter. Therefore, to obtain moles, you can multiply molarity by liters to obtain this amount due to this equation. So now that we have obtained our mole amounts, we can set up our BCA table. So our performed reaction is HN3 plus OH. And again, Na is a spectator in this case, therefore we can leave it out. This yields N3 minus plus H2O, also known as water. And again, this is a BCA table. So we know that we have 0.005 moles of HN3 and 0.001875 moles of OH. We also know that we have a 1-to-1 molar ratio, and this also is a 1-to-1 molar ratio. So our change, we have to look at the lowest amount here, because that is our limiting reactant. And in this regard, it is 0.001875, and so we will subtract that from the both reactants, and we will add it to our product. Upon doing this, we find that after we have 0.003125 moles HN3, 0 moles OH minus, and 0.001875 moles N3 minus. Next, we can finally calculate our pH. And we can do this utilizing the equation pH equals pKa plus log of our concentration of base over our concentration of acid. So once we do this, we find that pH equals, again, our pKa is 4.72 plus log of 0.01875 moles over 0.003125 moles, which we have obtained from our BCA chart. Once you perform this calculation, we find that the pH equals about 4.49815125. And using sig figs, this comes out to be 4.50.
Okay, so the next step, we're gonna titrate at equivalence points. We're adding 0.01333 liters of NaOH, which is equal to 13.33 milliliters. And to begin that, we find the initial moles of the HN3 and the NaOH. For HN3, it would be the 0.01 liter or 10 milliliters times the molarity, which is 0.50. You get 0.005 moles. For the NaOH, it's the 0.01333 liters times 0.375 molar, which we calculated at the beginning. And we find about 0.005 moles. And we use this information to make a BCA table. And we exclude the sodium ion because it's a spectator. We don't include water because it's a liquid. So we put the starting moles, which are equal to one another, and there's 0 moles of N3. And then we subtract 0.005 moles because that's the limiting amount of the reactants for both of them. And you find 0, both of these, and you add the same amount to the N3. So you get 0.005. So for the concentration of N3 that we need for the ice table that we're going to do, we use the 0.005 moles and divide it by the total mass, or total volume, and that would be the 0.01 liters of the acidic solution and the 0.01333 liters of the basic solution. And you would find it is 0.214 molar for the concentration. So the next step after the BCA table, we already found the concentration of N3 from the BCA table. And for that, to use that, we do an ice table this time. And we have N3 plus water goes to the acid. So it's the opposite reaction. And hydroxide ions. So we have an ice table. In the initial moles we have, or molarity, we have the 0.214 and 0 for each of these. And water is excluded because it's a liquid. And because this is a reactant, you would have minus X. And these are products, so you have plus X for both. So it would be 0.214 minus X for the molarity of N3. And it would be X for both HN3 and OH. So using that, we can find the pH by starting with finding the Kb value. And Kb equals Kw over Ka. And for Kw, we use 1.0 times 10 to the negative 14th, which is a given, over the Ka value, which is 1.9 times 10 to the negative 5th. And from that we find 5.26 times 10 to the negative 10th, which when we set this equal to x squared, which is found by the products, over 0.214 minus x, but because it's at the equivalence point, we assume this is so close to 0 is negligible. So we use this to find x, and using this equation, we find that x equals 1.06096 times 10 to the negative fifth. X is equal to concentration of OH, so we can find the POH using this value, which will equal negative log of X, which is 1.06096 times 10 to the negative fifth. And we find for the POH 4.97. So for the pH equals 14 minus POH, which is 4.97. So the pH is equal to 9.03. And we can verify all of this work by doing the 5% assumption. And I can do that right here, I believe. And we can just put the value we got for X, 1.06096 times 10 to the negative fifth, over 0.214, which is the moles of N3 to begin with. And we multiply that by 100 to find percentage. And that would equal 0.00496%, which is less than 5%. So the assumption is valid.
So as previously found, equivalence point occurs at the addition of 13.33 milliliters of NaOH. Therefore, to find the pH after equivalence point, we will be adding 18 milliliters of NaOH. So firstly, as with the other steps, before we can perform any calculations or set up a BCA table, we have to calculate the number of moles of our acid, HN3, as well as the number of moles of NaOH. So first we'll calculate the number of moles of hydrozoic acid that we have. And again, we know that our molarity for acid is 0.50 molar, and we can multiply that by our 10 milliliters, otherwise known as 0.01 liters, to obtain our mole value, which comes up to 0.005 moles of HN3, my apologies. Next, we'll calculate the number of moles of our base, our strong base, NaOH. As we found in the beginning of the video presentation, our molarity is 0.375 molar. And we multiply this by 18 milliliters divided by 1,000 milliliters in order to get our liter conversion. And once we do this, we find that we have 0.00675 moles of our strong base, NaOH. Now we can set up our BCA table. We know that the performed reaction in this case is HN3 plus OH minus yields N3 minus plus H2O. And again, H2O can be included or excluded because it is a liquid. And we know that our molar ratio is 1:1, and this is also 1:1. So as we've obtained up here, our starting mole value for HN3 is 0.005 moles, and that of OH minus is 0.00675 moles. And again, Na can be included or excluded. However, in this case, it is a spectator ion, so we decided to exclude it. And then we also have 0 moles starting out with of N3 minus. So again, looking at the least amount, it is 0.005, so that will be our limiting reactant, and that is what we will subtract from all components on our reactant side. Then we will add it to our product. Upon performing this calculation, we find that we have 0 moles left over of HN3 because it was converted all the way. And then we find that we have 0.00175 moles of OH minus and 0.005 moles of N3 minus. So to determine pH, we will utilize the concentration of our OH minus. So to find our concentration, we will take our mole amount, which obtained from the BCA table is 0.00175 moles, over our liter amount, which in this case would be 10 milliliters plus 18 milliliters, which comes out to 28 milliliters. Upon converting this, we find that it is equal to 0.028 liters, which is the conversion necessary for molarity. Upon doing this calculation, we find that our molarity is 0.0625 for our OH minus. We know that POH is equal to negative log of our concentration of OH, which in this case is 0.0625, and this is equal to 1.204 approximately. Then to obtain our pH, we will use the formula pH equals 14 minus our POH, which in this case is 1.204. Upon performing this calculation, we find that our pH after equivalence point, upon adding 18 milliliters of NaOH solution, is around 12.796, which regarding sig figs rounds out to be about 12.80. Next, we'll be discussing the importance of acid-base chemistry in the real world and real-life applications. Acid-base titration is important in various applications in the real world. In a pharmaceutical and research context, it is important to know how different acids and bases can affect and neutralize each other. For example, if the pH is changed of an acidic medication by adding a basic filler, this could change the effectiveness of the medication, as well as make the medication harmful in some ways. One important application of this effect is that some medications, like amphetamines, are basic, and if the person taking the medication has an overacidic meal or stomach biome, it can reduce the effectiveness of that medication. Acid-base titration is also utilized within the cosmetics industry due to the application of varying chemicals to produce different physical results. Many of these products have varying pHs and may have disastrous effects in pHs in combination. So acid-base chemistry is utilized to ensure the pH is appropriate for the body part it is being applied to. A real-life example of this would be the neutralization of acidic topical acne treatments with more basic moisturizers. Other uses of acid-base chemistry are existent within the cleaning industry. Many products of varying pHs that react differently with surface substances and liquids, and liquids to aid in decomposition, hence making the area cleaner. One real example of this would be the use of borax and baking soda. Since borax and baking soda are more alkaline, they're ideal for breaking down organics like dirt and oil. However, acid-base titration must be used to ensure that these products are not too corrosive that they damage surfaces. These are just a few of the many examples of real-life applications in regards to acid-base titration.